Hello everyone, my name is Siwan Seok. Today I will present my project, Retinosity Processing Platform. This software was developed using C++, OpenCV, and Qt6. The table of contents is as follows. Now I will start with the project goal. In the previous homework 3, I implemented an OCT signal processing pipeline. The pipeline converted raw interference signals into A scans and reconstructed a B scan image. I also used a frequency domain notch filter to reduce fixed pattern noise or FPN. In this project, I extended that idea from B scan reconstruction to interactive 3D OCT volume visualization and image processing. So the goal is not only to process one image, but to build a software platform that can explore and process a 3D OCT style volume. The project goals are shown here. The software loads a 3D OCT volume from 256 grayscale PNG B-scan images. It displays three orthogonal views: the XG B-scan view, the XYN and C-scan view, and the YZ cross-section view. It also shows a 3D schematic volume with the current slicing plane. In addition, it provides multiple image processing functions from the lectures. Now I'll explain the input data structure. The input data consists of 256 grayscale PNG B-scan images. Each PNG image is an XGB scan at a fixed Y position. By stacking these images along the Y direction, the software reconstructs 256 by 256 by 256 volume. The volume axes are defined as follows. X is the lateral direction, Y is the B-scan index or slow scan direction, and Z is the depth direction. The dataset is a simplified synthetic retinal OCT volume. It includes structures such as ILM, retina, photoreceptor, ONR, RPE, and chloride. It also includes artifacts and noise such as Gaussian noise, fixed pattern noise, and bright spot. This data set is used for software testing and visualization, not for clinical diagnosis. Now I'll move on to the project structure. This slide shows the file level project structure. The project contains main SQL book, main window, volume manager, processor, and renderer modules. Main window controls the Qt GUI, including button, slider, and panel updates. Volume manager loads the 256 PNG scans and extracts XY, XZ, and YG slices. Processor contains the image processing algorithms such as filtering, enhancement, segmentation, edge detection, and pseudocolor. Renderer draws the 3D schematic volume and the current slicing planes. This modular structure makes the program easier to understand and extend. Next, I will explain the software architecture. This slide shows the runtime data flow of the software. First, the retinal data folder provides the 256 PNG B scan stack. Volume Manager loads the image, manages the 3D volume, extracts XG, XY, and YG slices, YG views, and computes basic statistics. Main window works as a GUI controller. It receives user input from buttons and sliders and updates the panel. When processing is requested, main window calls processor. The processor performs filtering, enhancement, segmentation, and pseudocolor processing. Separately, renderer draws the 3D cube and current slicing planes. Finally, the processed views are displayed and can be saved as image file. Now, I will introduce the implemented image processing functions. The software includes several functions covered in the lecture. For filtering and enhancement, I implemented Gaussian, median, bilateral filtering, historical equalization, and unsharp masking. For filtering and Gaussian filtering smooths random noise and its sigma value is adjustable. Median filtering reduces speckle-like noise while preserving edges. Bilateral filtering performs edge-preserving smoothing. Histogram equalization improves contrast. Onshore masking enhances layer boundaries. For frequency domain processing, I implemented an FFT notch filter. It removes fixed parent noise using 2D FFT, Gaussian notch filter, and inverse FFT. For analysis and visualization, the software includes segmentation, Sobel edge detection, adaptive thresholding, and pseudo-color visualization. This slide shows an example of filtering and enhancement. The user can adjust filter parameters such as Gaussian sigma, median kernel size, bilateral stress, and onshore boost. Also, filters can be applied sequentially. This slide shows examples of FPN removal and analysis function. The FFT notch filter removes periodic fixed parent noise from the B-scan image, and the Sobel edge result highlights retinal layer boundaries using a red overlay. Next, I will summarize the key software features. There are four main software level features. First, the software supports multiplane OCT visualization. The user can inspect XG, XY, and YG view. Second, it provides 3D schematic rendering. The wireframe cube and colored slicing planes help user understand the current slice position. Third, it supports sequential processing. Filtering operations are applied to the B-scan stack, and multiple filters can be applied in order. Fourth, it saves the currently displayed result. This includes processed image segmentation result, edge overlays, and pseudo-color result. These features make the program closer to the interactive image processing platform, rather than a single function filter tool. Finally, I will conclude the presentation and briefly mention development tip. To conclude, this project implemented an interactive retinal OCT processing platform using C++, OpenCV, and Qt6. The software extends OCT processing from B-scan reconstruction to 3D volume visualization and image processing. The main achievements are multi-plane visualization, sequential filtering, FPN removal, segmentation, edge detection, pseudo-color visualization, and saving the display result. During development, several points were important. First, the software should be modularized. Second, the volume convention must be clearly defined. Third, original and processed data should be stored separately. This enables sequential filtering and resource operation. Final deployment should be tested early because an exe file alone is not enough for Qt and OpenCV software. That concludes the presentation. The full MATLAB code, no, let's start the demo. If you want to execute my code, follow the instruction in readme text file. Let's start the demo. First, we should move to the folder. We are in the retinal.exe folder, and we should move to in deploy folder, where in build file, I made it. So in build file, we can see the exe file. We don't have to build the whole code. You can just execute them by using this executive file. And next, we should open the folder in the retinal data. Retinal data have this B-scan image. we can see this 3D volume, XG view, XY view, and YG view. We can change it by sliding, and we can see the photoreceptor. We can see all layer by rendering. And next, we should use the filtering. First, apply the Gaussian filter. How about the 2.5 sigma? Then we can see the smooth Gaussian filtering. And sequentially, we can use the medium filter by corner size 3. Then maybe we can use more. You can see the change. And also, we can use histogram equalization. But you can see that in this Gaussian median histogram equalization can't reduce this FPN noise. So we can. We can reduce the FPN noise by this remove button, the FFT. So we can see the FPN are reduced in this page, in this slide, and you can see it applied to all depths. So and up by using bilateral 40. So we can see the more smooth but still have an edge. And if you want to more edge by using unsharp 4, then we can see more edge. Now we should apply the segmentation. If we do that, we can see in the photoreceptor layer, we can see the photoreceptor and other fluids or retinal tissue. And if you want to see the boundary of the tissue by using Sobel edge, then we can see that the tissue layer more precisely. And in the XY view, we can see the photoreceptor more clearly. We want to see. So by using adaptive threshold, we can see more clearly in this part, in this cell. Now, we should use the pseudo color. I FPN first. This pseudo color, I map the color to the different depths. And so if you perform the pseudo color, then we can see the shallow depths are mapping to a red one, and deeper depths are mapping to blue one. So if we change the slide, then we can see in the photoreceptor layer are green and more deeper. This PLA layer are green and more higher. We can see this retinal layer. So this is, and if you want to save the image by using the save button and choose the file, and you can download to any location. Then we can see in here. You can see here saved well. So this is my software tool. If you want to execute them, you just follow the README file. I write it more clearly, so just follow the instruction, then you can use my code. Thank you for listening.